Alrighty folks, in this video we're going to go over the concept of a first derivative test. Okay, so what is a first derivative test used for? It's used to help us determine where our function is either increasing, decreasing, and it's also going to help us locate any local minima or local maxima of our function. Before we get into all that, I want to make the relationship between derivatives and increasing and decreasing clear for you guys. So it turns out that a function is increasing everywhere the first derivative is positive. So those are synonymous. They mean the exact same thing. Increasing means that you have a positive first derivative. A negative first derivative means that your function is decreasing. Okay? And then a function is constant everywhere your first derivative is equal to 0. So I want you all to kind of get to the point where those are like synonymous, saying the exact same thing. Okay? All right, for example here, look at this graph that I've drawn here. And let's say that we have this graph here. And based off this graph, you'll be asked to do this in the homework. They may ask you something like this. They may ask you, hey, list all the values of x, and they want interval notation, such that f prime of x is positive. They want to know for what values of x is your first derivative positive. Well, that means, come over here, that means, look, we just want to know where the function is increasing. That's all that means. And for what values of x are we increasing? Well, if you look here, hopefully you can see my mouse, right here is where our function is increasing. Remember, you go to left to right, and if you're rising, you're increasing. So for what values of x are we increasing? Well, we're increasing from, this is interval notation, for x values in between -2 and 4. All right. So early in the semester, even in your college algebra class, they told you increasing, decreasing, always use parentheses. Well, now we can formally explain why that's the case. The reason why we use parentheses is because at -2 and at 4, our function is actually constant. It's neither increasing nor decreasing. Because it flattens out there, the derivative there is actually 0. Okay. All right. Same graph. What if instead they asked us to figure out where is our first derivative negative? AKA they want to know for what values of x are we decreasing? Okay. Well, we are decreasing from, remember these are x values, interval notation. Come over here. This branch of the graph is decreasing as we go from left to right. It's falling. So for what values of x? Remember, this arrow means we're going up forever, but that's not an x value. Going to the left tells us the x value there. So since we're going to the left infinitely, our function is going to be decreasing from -infinity until we get close to an x value of -2. Once again, for the reasons we discussed earlier, parentheses. But union, that's not the only place where we're decreasing. We're also decreasing along this branch of the graph right here. What values of x makes up that branch of the graph? It's from 4, not including the 4, to positive infinity. Why is it positive infinity? Because, don't let that down action fool you. X value is concerned about lefts and rights. This is going to the right infinitely. Okay. And then lastly, what if it said, hey, for what values of x is our derivative equal to 0? The first derivative. It's going to be constant. That's where our function is constant. Okay? All right. So then this time, it's not going to be interval notation. It's going to be specific values of x. All right? And as I said, this is where the graph kind of flattens out. Okay? And so here we have an x value of -2 and an x value of 4. That's where our function is constant. So I want to make sure this is clear that this is not interval notation. So let's do it like this. In fact, -2 and 4 will be the location of a local min and local max. Okay, that's going to come into play when we talk about the first derivative test. But let's go ahead and specify these now. What if we're asked, and what is the location of a local minimum? So a local min, I want you guys to get in the habit of recognizing this, is that a local min, as another term is relative min, it's located in what I call a mountain valley, right? So we need a valley in order for us to have a local min. That means we have increasing on both sides here. Anyways, x equals a -2 is the location of our local minimum. A local max is going to be located in a mountain peak, meaning you got to be at the peak and you're going to have both sides decreasing. All right. And so here at x equals 4, we have a local max. Okay. All right. So visually, that's what we're looking at, or I should say graphically. Okay. So now what the first derivative test does is going to allow us to perform the same analysis, but we could do all this without even looking at the graph. Before we do that, I have to introduce a new term here, and this term is called a critical point. So a critical point is the x value, has to be in the domain, that makes the first derivative either 0 or undefined. Okay, so the critical point is the x value of your derivative that makes sure that derivative either 0 or undefined. Okay, really quickly, so what does it mean to be undefined? Well, for you guys, the only way we're going to be undefined is if we take the derivative of a function and we end up with a fraction. Remember, we're trying to avoid having zeros in the denominators of these fractions. So any x value that creates a 0 in the denominator, that's going to make our function undefined. Okay, all right, here we go. For example here, suppose we have the following function. Okay, f of x is 8/3 x cubed plus 32x squared plus 120x plus 9. Let's say part A was we are asked to calculate any critical points. Okay, calculate any critical points. All right, well, in order to do that, our first step is to take the derivative, the first derivative. So here we go, 8/3 x cubed. So we're going to take that derivative. So 3 is going to multiply 8/3. 3 times 8/3, those 3's will cancel. We're left with the 8x squared plus 2 times 32 is a 64. X to the first. And the derivative of 120x is a 120. And the derivative of 9 is 0. All right. So there's our derivative. And our critical points are going to be anywhere this first derivative is undefined or equal to 0. Well, as we look at this function, this derivative is never going to be undefined. Okay, I mean, it's valid for all values of x. So the only time we're going to have a critical point is if this derivative equals 0. And so for you guys in this homework, that's going to be the vast majority of the way you get your critical points. Okay, you're just going to simply take your derivative and set it equal to 0. All right, now let's factor this. And the first thing we're going to look for is let's see if there's something in common. We got an 8, a 64, and a 120, so we can factor out an 8, I believe. So we have x squared plus 8x plus, let's see, 120 divided by 8 is 15. So that equals 0. And then we can continue to factor the parentheses. 8 times x plus 3 times x plus 5. Right? And then we're going to get two solutions here. X equals a -3, x equals a -5, and those are our critical points. Those are the values of x which create which makes our derivative become 0. Okay, let's say part B is that we're asked to figure out for what values of x, for what intervals is our function increasing and where is the function decreasing. Okay, all right, in order to do that, we're going to use the first derivative test. Let's do that. All right, and so what this is a number line, and this number line represents all x values from -infinity to +infinity. And what you got to do is you're going to put just your critical points on this number line here. Okay, make sure you put them in correct order here. So we're going to have -5, -3, and those are our two critical points. So remember, increasing, decreasing talks about intervals. So this left region over here represents all x values between -infinity and -5. Over here, we're in between -5 and -3. And right here, we're talking about all x values greater than a -3. Okay? So how do you actually use the first derivative test? Is that what you're going to do is you're going to grab a representative from each of the regions. Okay? Not the critical points, but a representative from each of the regions. And you're going to plug them into the first derivative. And then you're going to record the sign of the value that you get. Meaning if you get a negative sign, all right, we're going to write down a minus sign. If we get something positive, we're going to write down a plus. Let me show you what I mean. In this leftmost region over here, okay, our representative is, I'm going to use a -6. So we're going to take -6 and we're going to plug it into the first derivative. Very important. Plug it into the derivative. I could use a -7, a -12. It doesn't make any difference. It just has to be smaller than a -5. All right, this is what I'm going to do. I think I already have it preloaded, but let me go to y equals. So you go to y equals and you place your derivative into your y equals. Okay, just a quick way of evaluating this. And then we go to our table. Actually, let me go to my Windows setup. Okay, so hit second window, make sure that your independent is on ask. And then if we go to our graph here, or our table, excuse me, let's delete these out. I want to type in a -6. And so f prime of -6 is a positive 24. So what does that mean? That means I'm going to put a plus in here. That indicates that in this region, any x value between -infinity and -5, our first derivative is going to be positive, which means our function is increasing. Okay? Same thing. Here we go. Next one. In between -5 and -3, I'm going to use a -4. Okay. Let me show you a quick way. If you don't have a calculator, there's another way you can figure out the sign of this. What you do is, remember, all of these, you can see my mouse up there, all of these is the derivative. It's just, they just have different forms. And so what I'm going to do is, let me plug it into this factored form here. Let me plug -4 into that. So I have 8 times a -4 plus 3 times a -4 plus 5. Do a different color here. Okay, so then this is going to be 8, a positive 8, times some negative number, because a -4 plus 3 is a -1, but it's just negative, times another, times a positive, right? Because -4 plus 5 is a positive number. So a positive times a negative times a positive, right? Because the 8 is positive. Well, that's going to result in me having a product that is negative. Why is that? You know, if you have an odd number of negatives that you're multiplying, the resultant product is going to be negative. Okay, remember, this is a sign test. All I care about is the sign of that product there. Okay, and one more. I need a number that's bigger than a -3. We can use f prime of, let's say, 0. Okay, and I'm going to do the same little trick that I did before. We're going to have a positive 8 times, let's see here, 0 plus 3 times a 0 plus 5. Well, we got a positive 8 times another positive number times another positive number. Well, 3 positives, when we multiply those, we're going to end up with a product that is positive. Okay, so where are we increasing? We are increasing everywhere our first derivative is positive. That's indicated by a plus sign on our number line here. So we are increasing from -infinity up to -5. Remember, always parentheses are increasing, decreasing. And we're also increasing from -3 to positive infinity. All right. Where are we decreasing? We are decreasing everywhere we have a negative sign on our number line, and that's going to be in between -5 and -3. So remember, this is interval notation. All right. Here we go. Last little part here. We can also use this first sort of test, this number line, to determine the locations of any local mins or maxes. Okay. So remember, a local min and a local max occur at the critical points. I should make that a little note over here. Okay. Local, I call them local extrema, right? Extrema means both. Local extrema occur at critical points. In fact, it can only occur at critical points because we need that flattening out. We need that action there. All right, so let me erase our previous work here. And so to determine the location of any local min or max, what you do is you're going to draw a little picture around your analysis. What I mean by that is, okay, look at -5. What we said at -5 is that to the left, we said our first order is positive, means we're increasing. So to the left of -5, we're increasing. At -5, since it's a critical value, we flatten out for just that brief moment. And then to the right of -5, we go back to decreasing. You see that? So what happens at -5 is that we're going to have a local max. So we have a local max at x equals a -5 because we went from increasing to decreasing. At -3, to the left of -3, we are decreasing. At -3, we flatten because it's a critical point. And then to the right, our analysis said we have to increase. That creates that action, and we now have a local min at x equals a -3. Okay? All right, so that's how you use your first derivative test to determine increasing, decreasing in the location of any local extrema, min and max. All right, so the first step, though, is to find your critical points, and you do that by taking your first derivative and setting it equal to 0. And in a rare case, you may have to figure out where it's undefined, and that's where a fraction has a 0 in its denominator. All right, hope this helps you out with your homework. See you in the next video.